In this video, I'm going to begin discussing constant speed propellers that are used on light aircraft. And so this primarily applies to general aviation type aircraft. Around the college, things we have, the Cirrus use this type of a propeller, the Cessna 182, the Mooney M20, the Beechcraft Baron, all use these. We'll later on in the semester, we'll have a discussion of constant speed propellers and then look at some additional features that are incorporated on those that are used on larger transport category type aircraft. But today we're primarily going to be focusing on light aircraft. So the reason for a constant speed propeller is that in flight, while the aircraft is operating, the blade angle can be adjusted. And why this is important is that a blade of a given angle is only going to be ideal at a certain speed. And that could be RPM, rotational speed. It can also be a forward velocity. And so if we have these constant speed propellers where the blade angle is adjustable, where the engine and the propeller governor are able to make changes, we can increase or maximize the efficiency of that propeller in given situations. During things like takeoff and climb out, it's important to have a high amount of power available. The operator of the aircraft is using power to try to accelerate and to climb, but that's not the most efficient when it comes to things like fuel use. Once the aircraft is up and flying level and cruising essentially, or even during the descent phase, that power isn't as important, but what becomes important is maximizing the distance traveled for a given fuel burn, so fuel efficiency. And so these propellers, these constant speed propellers with adjustable blade angles allow that to happen. And so the way they do that is they're going to be looking at things like relative wind and angle of attack. And so I'm just going to do a quick review of that in the kind of the blank space we have here. If we look at our propeller on end, I'm going to start with takeoff. And so during takeoff, we have a relatively low blade angle. So here's the flat face of the blade, and then it's got the leading edge, and there's our propeller. So we're looking at the end of our propeller, and this propeller is going to be initially moving, with the engine just running. It'll be moving in one direction. It'll be rotating, and it will be rotating this way. And it'll be a fairly big velocity. The other thing that happens is as the plane starts to accelerate forward, and during the takeoff, roll, and climb, is that we will, the blade is moving this way. The aircraft will start to move this way. And initially, it'll be a small velocity, and then it'll get bigger as we go. But we'll start with a small velocity. So here is, this down arrow is the propeller moving in the downward direction. The blue arrow is the direction the airplane's moving, and right now it's fairly slow or fairly small. And that's going to result, the result of that is then we have the propeller is going to experience a wind or an air movement that's equal and opposite to these. And so what we end up getting is the rotation. There's going to be air, so now I'm drawing the air movement, equal and opposite here. And then there's going to be an air movement from the front that's equal and opposite going this direction here. Okay, so there's kind of two components of wind angle that this is going to experience. And so if we bring these down here, and they're going to kind of be covered up, if we bring our rotational movement and we bring our forward movement here, we end up with a resulting wind angle or relative wind that's going to look something like this. I'm actually going to bring this one up to the top, because then what we can do is our wind is going to be about here. So that's going to be our resultant relative wind. So if we put that against our blade here, here is our relative wind, and And then if I draw a chord line on our propeller, the chord line is going to go through the center line of the airfoil here. It's not perfect. There we go, relative, about like that. We're going to get an angle formed between these two, and that's going to be the angle of attack of the blade. So you can see right now that's fairly small. But what will happen is, as this starts to move, as the plane starts to pick up speed, that wind from the front is going to increase. Or once the airplane's in the air, that the amount or the velocity of the wind coming from ahead of the airplane, ahead of the propeller, is going to increase. It's going to get bigger. So remember, that was this little arrow pointing this way. That arrow maybe gets something like this, gets even bigger. And so what'll ultimately happen to the wind that's hitting the propeller is it's going to move forward as well. So our new wind angle might end up being something more like this. And now you can see, if that was the case, our angle of attack has almost gone negative. And so by being able to rotate this blade, we can maintain an angle of attack that's more ideal as that relative wind shifts. And so that's kind of getting into the cruise. So now so we started off with a low blade angle with a high RPM. We run our engine at high RPM. That gives us a lot of power. And then as the angle of attack gets closer and closer to the chord line of the blade, that's actually going to cause the RPM to get too fast. So it will begin to increase that angle of attack, or that blade angle, in order to maintain the angle of attack. And then at cruise, we can tell the crew, the pilot, we have the ability to tell the blade that we want to go to an even higher angle of attack, a bigger angle there between relative wind and chord line. And what that does is it increases the amount of air that's being accelerated for a given RPM, or it allows us to reduce the RPM that the engine's using to decrease fuel consumption. And so I do have a diagram, kind of a static diagram of this on the next slide that I'll show here right now. So here is that, what's happening. This is that forward velocity and the thrust we're getting, and then angle of attack between the relative wind. But you have to understand, as the RPM changes and as the forward velocity changes, that this relative wind is not always going to stay from the same direction. And so these constant speed propellers with variable blade angle are able to help to maintain and change that angle of attack to drive efficiency. As the operator runs the aircraft, they are going to have times where they need high power or need lower power, and so that's where the power change procedure comes in. And when we have an aircraft that has a constant speed propeller, most of the time it's going to have three controls in the cockpit. It's going to still have, it's for engine and propeller controls, mind you. It's going to have a power lever, a throttle, that's going to control engine RPM and engine power output by controlling, or essentially telling the carburetor or fuel injection system how much fuel to put into the engine. And then it's going to have its mixture control. So, even the fixed pitch propellers that we've looked at, or that you looked at in the past, have a throttle and a mixture control. But then these aircraft that have constant speed propellers are going to have a propeller control, or an prop RPM control. And so there's kind of a standard order or procedure that one would follow when operating an aircraft that has, and in this case, a reciprocating engine aircraft that has a constant speed propeller. So in a situation where power is being reduced, the first thing is we need to reduce the power that the engine's putting out. And so in that case, what happens is the the operator is going to decrease the manifold pressure by pulling back on the throttle. And remember, any of these controls, engine controls in an aircraft, you pull back to slow down, you push forward to get faster. Um, the that's the same is true for the propeller control. You push that control forward to make the propeller spin faster, which decreases blade angle. You pull that propeller lever back to decrease RPM, which increases the blade angle. So in this case, we're reducing power. We're going to slow the propeller down as well. So we pull back on the propeller lever. This increases the blade angle. And that propeller, as it starts to take a bigger bite out of the air, that's going to put more resistance on it, and it's going to slow it down. So that slowing it down is going to, that increased resistance is going to slow the engine down as well, in addition to the fact that we've reduced the amount of fuel going to it, and reduced the manifold pressure. On the flip side to that, the opposite is true if we want to increase power. And so first we want to be able to let that engine speed up and increase in RPM, which results in an increase in power. And so in order to do that, we need to get the propeller spinning faster. So we decrease the propeller blade angle by pushing the propeller lever forward. And again, pushing the propeller lever, it's going to make the propeller go faster. We push to go faster, we pull to slow down. And that's going to decrease the blade angle. And decreasing the blade angle reduces the amount of drag and wind resistance on the propeller, which allows it to spin faster. Then as the operator, we're going to increase the manifold pressure by pushing the throttle forward. And now, because the engine's running faster, we have an increase in power and an increase in RPM. And so this is that takeoff and climb scenario where we're using more fuel, higher RPM, developing more power to get the airplane accelerating and off the ground. The power reduction occurs then once the airplane is up to the altitude where the pilot or operator wants to cruise at, or even during a descent. The engine power needs to be reduced, and that's where you would do the first half of this. What's allowing this to all be done, or what's controlling this, is a component mounted to the engine. It's typically near the front of the engine, called the propeller governor. And the propeller governor is what actually essentially controls the blade angle. So, as an operator, as a pilot or a maintenance technician, you do have a propeller lever, and in a sense you control the propeller, but you really don't control the propeller angle directly. What you're doing is sending an input signal to the governor telling it what you want the propeller to do, whether you want it to go faster or slower, or whether you want it to increase angle or decrease angle. But at the end of the day, the governor is what actually performs this function. So you can almost think of the propeller lever as kind of a request. You're making a request of the propeller governor when you move the propeller lever. And so it will make changes to the RPM based on what you're requesting as the operator. It will also make changes to RPM throughout operation as the engine's operating, particularly in like a steady state thing where you're not changing. If the throttle position's not being changed, mixture is not being changed, propeller lever is not being changed, the governor is still there doing a job, because it has to make changes all the time to vary for changes in wind speed if you get gusts from the front or from the back, or angle, as the angle of attack of the aircraft changes, it's going to speed up or slow down, which changes the amount of resistance on the propeller. And so this propeller governor, is going to be constantly making these adjustments to keep the propeller spinning at a constant speed, hence the term constant speed propeller. And this is when it's in what's called a governed condition. So if a plane is operating, it's flying along level, there's no real changes, the operator hasn't done anything, but there's something that happens. You get a wind, you get a headwind or a tailwind or a slight change in pitch of the aircraft. If the propeller starts to increase, if the RPM of the propeller begins to increase, Say it can be because the plane nose gets pushed down and starts moving a little faster, which is going to decrease the load on the propeller, or you get a headwind, a gust towards the front of the airplane. That'll reduce the resistance on the propeller. It'll cause it to begin to spin faster. The RPM will increase. And so what's going to happen is there's the propeller governor is a hydromechanical unit. It has a set of flyweights inside of it. And when that propeller and the engine start to turn faster, those flyweights will be drawn out by centrifugal force, and they will port oil to, or they typically use engine oil to control this propeller blade angle. They will port or cut off the supply of oil depending on the design of the propeller in order to drive the blades to a higher angle of attack, a higher blade angle, which results in a higher angle of attack. So they'll increase the blade angle, and what that'll do is increase the air resistance on the propeller. It'll be having to take a bigger bite of air. That puts more resistance on it spinning, resistance to spin, and the propeller will slow down a little bit, and then that will send that signal, that rotational signal with the flyweights will feed back to the governor, letting it know that it's slowed down. The flip side, the opposite effect takes place is if the propeller is, if all of a sudden, if the nose starts to pitch up a little bit and the propeller has to work harder, or if there's a tailwind and that kind of helps to, that kind of puts some resistance on the propeller's ability to turn, that's going to slow it down. The prop governor will sense that, the flyweights in it will sense that, and it will port or cut off oil supply to the propeller in order to drive the blades to a lower blade angle, lower angle of attack. And that decrease in blade angle will reduce the amount of resistance on the blades to spinning. And so then the engine will speed up, the propeller will speed up to counteract that tendency. And so that's in a governed situation when things are, smooth. The other part of that is if an operator, makes adjustments, if the pilot or a maintenance technician reaches over and moves the propeller control lever, that tells the governor you want the RPM to increase or decrease. And so then the governor will, it'll say, okay, here's a new point to shoot for, a new RPM speed I want. I want it to go faster if I push the lever forward, or I want the propeller to slow down, I pull it back. And the propeller governor then is going to adjust the blade angle accordingly to reach that new RPM, that new speed. So if I've pushed the lever forward, which means I've requested or told the airplane I want the propeller to spin faster, the governor will then control the blades, will drive the blades to a lower pitch setting, and that will allow the propeller to speed up because there's, again, less air resistance to rotation. Or if I pull back on that lever and I tell the governor that I want the propeller to slow down, it will then drive the blades to a higher blade angle, taking a bigger bite of air, putting more resistance on it, and slowing the propeller down. There is one other situation that we can have, and that's when we get outside of what's known as the governed range. And so essentially what happens is if we slow the engine down to a point where essentially the blades go to the lowest angle that they're able to go to, if the propeller goes to the lowest blade angle possible, and we're not giving enough power to the engine to maintain the speed that we've selected, the governor at that point is just going to hold those blades in a low pitch position. So that's what's called a non-governed condition. And so now the governor says, okay, I can't maintain, say the position of the lever of the propeller lever would normally would normally tie to, or would normally be about 1500 RPM, and the max at low blade angle that the engine can put out now is 1200 RPM. Well, the governor is just going to essentially hold those blades in that fine pitch low blade angle. And the propeller at that point acts like a fixed pitch propeller, where by increasing or decreasing the throttle, the amount of power the engine's putting out, the propeller will speed up or slow down, but it's now below that governed range. And so these propellers at lower RPMs act like a fixed pitch propeller, but then once they get up into the what's called the governed range, then that's where the propeller governor kicks in and can maintain a certain speed. And so that's what kind of is shown at the bottom of the slide there. In the next video and lecture, we'll get into kind of describing how the system works with the propeller governor. Here you can see an engine with the propeller governor and then the propeller, and how these work together to actually make these pitch changes take place.